work energy theorem. In this topic, I just want to define the kinetic energy of an object, and then later we gonna try to relate the work done by the resultant force or the net force. Okay, so let's use the symbol as the W net here for the work done by the resultant force and the change in the kinetic energy of the object. Let's consider these figures. So okay, this is going to be the trajectory of the path of the object moving on this line, and then let's say that this one is going to be the vector position of the initial position of the object. Is going to be the Ri, and then here is going to be the vector position, the R2. Sorry, let me just make this one to be the R1. Okay, the R1 and the R2 for the initial position and the final position, and then the object just move along this path, right? So now let's consider just an interval here. Okay, so let's see that we have these intervals with the displacement equal to the dr, and then the force exerting on this object, right? So just go into this direction. So this is the resultant force or the net force exerting on the object. So now we just want to find the work done by the net force or the resultant force. Actually, we have seen this one already from this equation. Okay, from this equation, then we can get that the work done. Okay, the work done by the resultant force is W net, right? So it's with the symbol that we use here, equal to the integral of the net force, and then dot product with the dr, right? And then just make the integral from the Ri from the R1 and then to the R2. Okay, from the R1 to the R2. So right now I'm just using this equation, but just change from the net force and then the work done by the net force here. But now we just want to find what? Okay, so let's consider here the work done by the net force in the infinitesimal displacement dr is, okay, so if we just consider just the small displacement here, okay, if we just consider the small displacement here, we can get that dw, okay, dw net. So this is going to be the work done in this region, very small region here, equal to the net force and then dot product with the dr, right? Okay, so it means that this term, we can think that this term is just equal to the work done by the net force, right? Okay, but now we say that from Newton's second law, right? From Newton's second law, the net force equal to the mass m and then times the acceleration. So we can just plug in this into this equation, and we get that equal to the m times the a and dot product with the dr. Okay, and then again we say that the acceleration, right, is just equal to dv by dt. Okay, acceleration just equal to dv by dt. So we can just plug in this into this equation, and then we have m and then times the dv by dt dot product with the dr. So now let's just move the dt to combine with dr here, right? Then we have that this is going to be equal to the m times the dv and then dot product with the dr by dt. Okay, so what is the dr by dt? We say that v, right, equal to the dr by dt by definition. Okay, so it means that in this case we can get the m times dv and then dot product with the velocity v. Okay, so what's next? Let's consider this. If we have the derivative of the v dot v, okay, if we have derivative of the v dot v, it's going to be equal to what? It's going to be equal to, okay, then we need to take derivative of the first one, right? And then plus the second one. So we have dv, okay, dot product with the v. So this is derivative of the first one. So now for the second one, right, we have plus the v and then dot dv. But now we say that we can just switch the position of the dot product. Okay, so in this case this term and this term just the same things, right? So then we have the 2 times the dv dot dv. Okay, so now you can see that dv dot dv, right, it's just this one. This is the dv dot dv. Then we can just plug in this into this equation, and then it's going to be equal to 1/2 times the m. Okay, the 1/2 times the m, and then times derivative of the v dot the v. V dot v equal to what? V dot v just equal to v square, right? Just equal to v square. Then here we have that equal to the 1/2 times the m and then times derivative of the v square. Okay, 1/2 m just constant. Then we can just bring this into this parenthesis, right? We can just bring the 1/2 times m into this parenthesis here. It's going to be equal to derivative of the 1/2 times the m and then times v square. Okay, then okay, let's try to make the integral both sides of the equation, because don't forget that on the left hand side here we have derivative of the work done by net force, right? So let's just make the integral both sides of the equation. So we have the work done by net force equal to the integral of the 1/2 m equal to derivative of the 1/2 times the mv square, right? Okay, then finally it's gonna be, let me just write down here, it's gonna be equal to 1/2 times m and the v2 square and then minus 1/2 times the m and the v1 square, right? Where the v1 and the v2 are just the speed of the object, right, at the position r1 and the position r2. Okay, so let me just write down here. Let's say that, for example, this can be the v1, okay, the velocity of the object at the position r1, and then here it's going to be the this will be the v2, the velocity of the object at the position r2 here. Okay, so now at this point we can define, Okay, at this point we can define the kinetic energy of a body, right, of a body with the mass equal to the m, and then moving with velocity v. Okay, so let's define the kinetic energy of a body with the mass m moving with the velocity v here. We use the symbol as k equal to the 1/2 mv square. Okay, this is the kinetic energy of the object. K equal to the 1/2 mv square. Then if you have the unit as, okay, so you can see, right, the mass is kilogram and the v is velocity, right, meter per second. But now we have the v square, so it's going to be equal to the meter square and then over the second square, which is equal to joules. Okay, or we use symbol as the capital J. Then this will be the definition of the kinetic energy. And then finally we can have the work energy theorem. Okay, we can have the work energy theorem to be, okay, the work done by net force, this one, the work done by net force equal to, okay, so now you can see that this one is going to be the final kinetic energy and this is going to be the initial kinetic energy, right? So this term, let's say that it just equal to the K2, the final kinetic energy, and then this term is just equal to the K1, right, the initial kinetic energy. Then we can have the work done by net force equal to delta K, okay, the change in the kinetic energy, which is equal to the K2 minus the K1. So don't forget that in the physics, right, when we use the delta symbol here, it means that it's going to be the final minus the initial. Then in this case we have the final kinetic energy and then minus the initial kinetic energy, which is equal to the 1/2 times m v2 square minus 1/2 times the m and then the v1 square, and that's it. So this is called the work energy theorem, or sometimes we just call it as the work kinetic energy theorem. But just keep in mind that, for this question, right, the left hand side here, it must be the work done by resultant force or the net force. It's not the work done by individual force, okay? It must be the work done by the resultant force. So in this case, we can see that if the K2 is greater than the K1, it means that the final kinetic energy is greater than the initial kinetic energy, right? Or on the other hand, we can say that the final speed is greater than the initial speed. Okay, it means that the body, right, will gain the energy. Okay, the body will gain the energy because the K2, the final kinetic energy, is greater than the initial kinetic energy. Okay, on the other hand, if the K2 is less than the K1, okay, if the K2 is less than the K1, it means that the final kinetic energy is less than the initial kinetic energy, or we can say that the final speed or the final velocity is less than the initial speed or the initial velocity. Then in this case, the body will lose energy and then the object will move slower, right? In this case, the object will move faster. Okay, one thing that I forgot to tell, okay, about the physical meaning of the kinetic energy. The kinetic energy is to be an energy that an object or a body just occupies, okay, or the possesses as it's moving. Okay, So it means that if the object is moving, it will have the kinetic energy. But then if the object is at rest, velocity equal to 0, so it doesn't have the kinetic energy anymore. Let's consider these examples. A student pushes a 8.0 kilogram box on the smooth horizontal surface with the variable force, right? The F equal to the 2.0 times the x Newton. So the x is the position of the box in the meters. The box initially at rest is pushed from the origin to the position x equal to the 5 meter. So calculate the box speed at this position. Okay, so in this case we have let's say that we have the smooth surface. Okay, we have the smooth surface here, and then we have a box. Okay, so we have a box. So initially at rest, so we have the 0 meter per second, and then it's going to be at the origin, right? So here x equal to 0. So then later on, the block will be at this position. Okay, so this will be when the x equal to the 5.0 meter. So we just want to find what? We just want to find the final speed of the block. Okay, we just want to find this v. But now we say that during the motion, right, we have the force F. Okay, we have the force equal to the 2.0 x exerting on the box here. Okay, so now let's try to use the actually in this case, right, we can just do the two approaches to solve for this one. The first one, we can use equations of the motion for the one-dimensional motion to solve for this. Or the second one, we can just use the work energy theorem to solve for this one. Okay, so let's use the first approach. Okay, so use the equations. No, wait, can we use equation? No, just go to the basic. Okay, so let's use Newton's second law. Sorry, I forgot that we cannot use the equations of the motion because the force is not constant. It means that the acceleration is not constant as well. Okay, so we need to go back to the basic using the Newton's second law here. Okay, now first of all, let's try to find the net force. Okay, let's try to find the net force. What forces do we have in this case? Okay, we have mg, right? We have the weight here, and then we have the normal force. Okay, we have the weight and the normal force, but you can see that the normal force and the weight just cancel out. It means that the force that we only have is this one, so this will be the resultant force. We have net force equal to the 2.0x, right, which is just equal to the m and then times the acceleration. Okay, so now we just want to find the velocity v. Okay, we just want to find the velocity v. Then we need an equation that changes the acceleration to the v. What do we have here? We have a, right, equal to dv by dt, and then we have a equal to v dv by dx, right? Okay, so now the left hand side of the equation, you can see that we have the x, the position, as the variable, right? We don't have time, then we cannot use this one. Okay, so let's just take this one out. We cannot use this one. We need to use this. Okay, we need to use this. So let's just plug it in, right? We have the m times the v and dv by dx. So then let's just move the dx here, right, to the left hand side of the equation. So because we just want to combine the same variables on the same side of the equation, then we have, okay, v dv equal to, this one is v dv equal to the 2 pi o over the m, and then times the x dx, right? Now integrate both sides of the equations. Okay, so when the x equal to 0, the velocity equal to 0 as well, right? 0 to 0 here. So now for an arbitrary x, we have the velocity v depending on the x as well. Okay, so then on the left hand side, okay, I will go really fast. I think you have seen this many times already. It's going to be equal to the v square, right? The v square, and then over 2 equal to. So now on the right hand side, right, we have the 2 pi o over the m, and then times the x square over 2. Okay, or we can get that the vx is going to be equal to the square root of the 2 pi o over the m. The m is the 8 pi o kilogram, right? And then times the x, and that's it. Okay, so now we can get the velocity as a function of the position x. But now we just want to find what? We just want to find the velocity, right, when the x equal to the 5 meter. Okay, let's just sub it in. So we said that at x equal to the 5 pi o meter, we can get the velocity equal to the square root of the 2 pi o and then over the 8 pi o square root, and then times the 5 pi o, which is equal to the 2.5 meter per second. So this is the answer. Okay, this is the answer. So this will be the first approach that we can use to solve for the speed, right? So now the second approach is, okay, so let's use work energy theorem. Okay, so let's use the work energy theorem to solve for this one. For the work energy theorem, we need to find the work done by net force, right? We need to find the work done by net force. Okay, then again, the work done by net force equal to the integral of the net force, and then times the dx, right? In this case, just equal to the dx, equal to, right, the integral of, okay, the net force equal to what? Equal to the 2.0x, the 2.0x, and then times the dx, right? So we just make the integral from 0 initially, and then to the 5, let's say to x first. Okay, to the x first here. Okay, now in this case, we can see that the work done by the net force is going to be equal to the 1.0 times the x square, and that's it. We have it as the joule, right, in this case. So then from the work energy theorem, the work done by net force equal to the 1/2 the m the v2 square, right, and then minus the 1/2 m and the v1 square. But we say that the object just start moving from rest, right? So v1 equal to the 0. Okay, so now just plug everything in. We have the 1.0 times the x square equal to the 1/2 and the mass m is just equal to the x point o, right? And then times v2 square. So v2 is the vx, right? And then square. So then finally you can get that the vx is equal to the square root the 2.0 and then over the x point o, right? And then times the x square. Okay, so now you can see that this equation, times x. This equation, right, just the same as this one. Okay, so now we just use the two approaches and we just got the same equation. So it means that at the x equal to the 5 meter, we can get the same velocity v as well.